And the goals for today, we're going to describe the fixed effect and random effects models and the underlying assumptions. So these two types of models are the commonly used statistical models for meta-analysis. And then we're going to show you how to compute the summary effect, the diamond down on the forest plot, using a fixed effect and a random effects models. So to begin with, let's have a quick review of what is a meta-analysis. Well, meta-analysis is an optional component of a systematic review, which means not every single systematic review would have a meta-analysis, although every single systematic review would have the qualitative synthesis. There are classic definitions for meta-analysis, which is the statistical analysis of a large collection of analysis results from individual studies for the purpose of integrating the findings. A better alternative definition is that meta-analysis is a statistical analysis which combines the results of several independent studies considered by the analyst to be combinable. So the second part of this definition, considered by the analyst to be combinable, is very important because you, as a systematic reviewer, has to make the decision whether the studies are similar enough to be put together in a meta-analysis. Meta-analysis is not that complicated. Let's demystify what is a meta-analysis. So for meta-analysis, you're including a set of individual independent studies. And in each study, those individual studies, the measures of association or the effect estimate of the treatment effect or the association is usually summarized as a risk ratio, as an odds ratio, mean difference, prevalence, or regression coefficient. For example, let's say we're doing a study comparing vitamin D versus placebo for preventing fracture, and then the fracture event will be a binary outcome. We can summarize that using risk ratio or odds ratio. And then you will have a set of studies to be included into your meta-analysis. Each study will have that summary measure. And now what we're doing in a meta-analysis is to estimate the overall measure of effect as an average. There are different ways to average a bunch of numbers. Arithmetic mean is one way, but in meta-analysis, we're taking weighted average. So the weight reflects the varying importance of each study in your meta-analysis. As you can imagine, we're going to assign more weight if there's more information in that particular study. And the more information is primarily affected by your sample size, as well as the number of events that occurred in that study. So more information will lead to increased precision in your individual study, and more precision overall will lead to increased precision in your meta-analysis results. In today's lecture, we're going to introduce two types of models for meta-analysis. We're going to start with the fixed effect model because that's simpler to describe and to introduce the concept to you, and then we will move on to the random effects model. Under the fixed effect model, we assume that all studies you're including in your meta-analysis are measuring the same common true effect size. Well, what does that mean? It means that if it's not for random or sampling error, all results in those individual studies would be identical. And now we're going to denote the true unknown effect size by theta. Okay, so basically the idea is saying we observe some effects from each individual study, and now we have to come up with a summary effect. And how we're going to do it? We're going to make some assumptions. And under the fixed effect model, we assume that each individual study estimated a true common effect size. Here is another way to look at the assumption. In this example, we have 3 studies. And each circle on the figure represents the true effect in each study. And again, under the fixed effect model, we assume all the circles coincide with each other, and we're trying to estimate that combined true effect. Well, the problem is, if we already know the true effect size in each study, we don't have to do any research at all, because we just take where that circle is and go with it. Again, the true effect we denoted use theta, and in this particular example, the theta is 0.6. So we don't know the true effect size in each study. What we have from your data is the observed effect size. And it usually varies from one study to the next. And under that model, the fixed effect model, we assume that there's only one source of variation, which is the random errors inherent in each study. If you look at the figure, the second figure on the plot, where we have the square, the black square, to represent the observed effect size from each study. So here, that's what you have actually from your study. Going back to the example, let's say we're comparing vitamin D versus placebo to prevent fracture, right? And you have 3 studies. You may observe the effect size of 0.4 in study 1, effect size of 0.7 in study 2, and the effect size of 0.5 in study 3. That's what you actually have from your data. And the purpose of doing a meta-analysis is trying to use those observed effect size to make the best guess of where the common combined true effect size is. Again, here, for example, the observed effect in study 2 is circled on the figure, and it's 0.7 in this example. The observed effect size varies from one study to the next only because of the random error inherent in each study. That's the assumption for the fixed effect model meta-analysis. And the sampling error, which is denoted as epsilon in this example, is minus 0.2, 0.1, and minus 0.1 respectively in study 1, 2, and 3. Another way to look at this data, so for study 1, the effect size you observe is actually 0.4. So y1 would equals 0.4. And how is that derived? It's using the overall mean theta 0.6 minus 0.2. That's your y1. And if you look at the second study, the observed effect size in that study is 0.7, and it can be written as using the overall theta 0.6 plus the 0.1, which is epsilon 2. And you can do the same for the third study. More generally, you can write this out, right? The observed effect size yi for any study is given by the population mean plus the sampling error in that study. So again, in a more general way, you can write yi equals theta plus the epsilon y. Then epsilon y is the random error or the sampling error inherent in that study. If you have 3 studies in your meta-analysis, the I would be 1, 2, or 3. Just to summarize, under a fixed effect model, there's only one source of variance, and that is the random errors inherent in the study. Here, if you look at this figure, we have the distribution of the random errors inherent in the study. Each normal curve on the figure reflects the amount of variance in that study. Comparing study 1 to 3, which study has the largest variance? Well, it's the first study because the normal distribution has the widest spread. And the study 2 is the most precise because the normal curve has a shorter distribution. And under the fixed effect model, we assume all the circles on the figure, which are the true effect from each study, but you don't see them, coincide with each other, okay? So you don't actually see the true effect from each study. All you see or all you have from your data is the observed effect size, which are represented as the square on this plot. So meta-analysis is basically you have all these numbers. You get a point estimate from each study as well as some variance estimate from that study, reflected as the width of the distribution of the normal curve on this figure. And now you're saying, basically you're telling your computer model or software program, well, I'm going to assume all the true effects in the studies lying on the same line together. And we're going to use that model to try to figure out where that theta is. So that's what you're doing under a fixed effect model. You're making the assumption all the circles, the true effect, that the unobserved true effect in each study lying on top of each other. So they're identical, basically. And to do a meta-analysis, you start with the observed effects and try to estimate the population effect through computing a weighted mean. Okay? So we say you have that estimate from each individual study, and now we're going to take a weighted mean to try to figure out where those circles are. And the weight assigned to each study in a fixed effect meta-analysis equals the inverse of the within study variance. That's the first equation on this slide. Wi equals the inverse of the variance for that study I. Okay, so now you get the weight for each study, which is the inverse of the winning study variance. And the weighted mean can be computed using the second equation on this slide, which equals the summation of yi, which is the effect size from that study I, times the weight I from that study, and you're going to sum across all studies included in your meta-analysis. That's your numerator. And the denominator basically is the summation of all weight. So let's say, going back to the previous example where you have 3 studies, then you will use the effect size from study 1 times the weight from study 1 plus the effect size from study 2 times the weight from study 2 plus the effect size from the third study, the last study, times the weight of that study. So that's your numerator. You do the same for your denominator, and that's how you compute the weighted mean. Getting a weighted mean is not sufficient because we also want to know how precise is that weighted mean. That's why you need to get the variance for the summary effect, which is the third equation on our slide. So the variance for the summary effect, the weighted mean, equals 1 over the summation of weight I. Again, if you have 3 studies, then your denominator would be weight 1 plus weight 2 plus weight 3. Once you get the variance, the standard error is basically the square root of your variance. That's the last equation on the slide. So those are the equations, all you need to know of how to calculate a meta-analysis results under a fixed effect model. And with those numbers, you can derive the 95% confidence interval. Again, the lower and upper limits for the summary effect would be the mean minus 1.96 times the standard error, or the mean plus 1.96 times the standard error for the upper limit. And you can use, again, the mean and the variance, or the standard error, to test for the null hypothesis that the common true effect size theta is 0. And from there, you can get the p-value. So the equations on these slides are standard equations probably you have seen already from your epi or biostats classes. Now we're going to plug in some numbers to the equations I just showed you and see how these play out. So here we have a data set where each row is the number or the results from one study. Together we have 6 studies. And for each trial, there are treated participants and untreated participants, the comparison group. And you will have the number of events and non-events from each group denoted as A, B, C, D in this data set. For example, for the first study, under the treated group, there are 12 events and 53 non-events. And under the control group, there are 16 events and 49 non-events. Going back to the vitamin D example, this could be the number of fractures. There are 12 fractures under those treated by vitamin D and 16 fractures under those who are treated by placebo. And that's the number you're going to get from each study. And altogether, we have 6 of them. Now, once you have these numbers, you can calculate the measures for the treatment effect. One of the measures is odds ratio. And odds ratio is defined as the odds of the event under one group over the odds of event for the other group. And if you remember the equation from your biostats class, so here the odds ratio basically equals AD over BC. And again, for the first study, if you plug in the 4 numbers, 12, 53, 16, and 49, you will get an odds ratio 0.69. So that's the first number on the second table here. And because this is ratio, and we work on the log scale, so you're going to take the log of that odds ratio and get a minus 0.37 for the first study. And the variance for odds ratio, again, you can go back to your biostats materials to figure out the equation. Again, you plug in those 4 numbers, you get the variance for that study. And remember from the previous slide, we said under the fixed effect meta-analysis model, the weight equals 1 over the variance. So for the first study, if you use 1 divided by 0.19, you're going to get the weight for that study, which is 5.4. Okay? And once you multiply your weight from that study with the point estimate from that study, you get your last column. So weight 1 is 5.4 and yi is minus 0.37. So you times those two numbers, multiply those two numbers, you're going to get minus 1.97. So that's what you get from your first study. And you do the same for the second to the sixth study. So you're going to fill in the numbers to this table following the same procedure and equations. You don't have to do this by hand. I mean, the easy way to do it would be to do it in an Excel spreadsheet where you plug in the equations and it will do it automatically for you. Or you use statistical software we're going to introduce later, for example, using Stata for the analysis. You don't have to do this by hand. And the most important thing on this slide is the sum of the numbers. So if you look at the last two columns, right? And those are the two columns we have to sum them across studies to get the summation. And why we need those two numbers? It's because, remember the equation to get the pooled odds ratio? So for the meta-analysis, you have to take the weighted average of those numbers. And the equation says the log odds ratio for the meta-analysis equals the summation yi times wi divided by the summation of wi. So that's why those two sums are important. And if you go back to the previous slide, or if you still remember the two numbers from the previous slide, they are minus 30.59 divided by 42.25. So that's how you get the log odds ratio of minus 0.72. And if we exponentiate that number, we get the odds ratio on the natural scale. So that's how you get your meta-analysis results. Remember we said you not only need the point estimate, you still need some estimation of the variability of that estimate. So how precise is that odds ratio? And in order to get the variance and confidence intervals, the variance of that log odds ratio equals 1 over the summation of wi. This is not a new equation. You have seen it on one of the previous slides. Again, we're just plugging the number from the example, and using 1 divided by 42.25, you get the variance. Square root of the variance is your standard error. And now again, plugging the numbers to the equations you're pretty familiar with by now, you will get the lower and upper confidence limit for the odds ratio. Fortunately, we don't have to do all this by hand, but I do want to show you how the calculation was done behind the scene. If you're going to do this using statistical software, this is what you will get most likely, which is a forest plot. Here, again, each row represents one study. We have the point estimate, the odds ratio from each individual study, as well as the relative weight that study is taking. So we calculated the odds ratio for the first study, which is 0.69, and the relative weight basically is the weight, the absolute weight of that study divided by the summation of weights across all studies. So the first study takes about 13% of all weight in the combined estimate. And each square on the right-hand side basically plots where the odds ratio is and the 95% confidence interval for that study. You will notice the size of the square differ, and it's reflected by the relative weight. So the fourth study, the Lane study, which takes about 41% of the total weight, is the largest, so it dominates other studies. That's why it has a larger square. And then the summary effect is shown on the bottom with a diamond, and the length of that diamond is the confidence interval for the results. So here the summary estimate is 0.46, and it ranges from 0.3 something to maybe 6 or 7. And you can get that number from our previous slide. So that's it for a fixed effect meta-analysis. And I think the most important thing you should take away from the fixed effect model is the assumption. Basically, we're assuming all studies in the analysis share a common true effect. And remember all the circles on the plot I showed you early on. We are assuming all the true effects line on top of each other. And the meta-analytical result is our estimate of this common effect. In other sense, all the observed variation reflects the sampling error. So the true effect line on top of each other, and all the differences you actually see from one study to the next is only because of the sampling error or the random error in each individual study. And the study weights are assigned proportional to the inverse of the winning study variance. So how precisely the estimates are. So the larger the study, the smaller the variance. So the larger study will contribute more information to the meta-analysis results, so it will take up more weight in your pooled estimate. That's a summary of the fixed effect model. We discussed the fixed effect model in the previous section, and now we're going to talk about random effects model. We're going to see how random effects model is different from the fixed effect model, and we're going to contrast those models throughout this section of the lecture. A quick review. Under a fixed effect model, we assume that all the studies are identical and the true effect size is exactly the same in all studies. Well, then the question is, how plausible is that assumption? Is the assumption underlying a fixed effect model plausible? What do you think? Well, then you're going to tell me we have to look at the studies and trying to figure out whether the studies are similar or different. Exactly, that's what you do. For example, the magnitude of the impact of an educational intervention might vary depending on the class size, the age, and other factors, which are likely to vary from study to study. So let's think about this for a moment. Who on earth are going to do a study that is exactly the same as a study that has already been done? You may get two identical studies for those drug trials submitted to regulatory agency for approval. So for example, for a drug to be licensed in the United States, the drug company have to do two identical trials and submit the results to the FDA. In that case, you may get two identical studies. But for most part, what you're going to have for your systematic review and meta-analysis are different studies done by different investigators in different places. We may or may not know for sure whether these characteristics are actually related to the effect size. For example, you may argue that vitamin D studies done in the United States are going to be different from those studies done in Asia because some countries may be more closer to equator such that they will have more sun exposure. So their vitamin D level, the baseline level in the participants are different. So we have all this knowledge to help us to evaluate the factors that may or may not be the same across studies. But for most time, logic suggests that such factors do exist and will lead to variations to the magnitude of effect. So what we're looking at, we're looking at the characteristics of the study. It could be design characteristics or the characteristics of the study participants for a study setting, for example. And these characteristics may be related to the effect size. So that's all we care about. We care about these characteristics because they may have effect on the effect size we're going to see in those studies. Here is an example from one of the class projects back in 2011. So this study looked at the association between the duration of breastfeeding and the risk of childhood obesity. So the hypothesis is that the duration is associated with the childhood of overweight. And here is what the review group found. Our 21 studies were all cohort studies, of which 8 were in the US, 9 in Europe, and 4 in Asia, Australia, or the Middle East. The studies analyzed breastfeeding duration ranges from as little as 0 to 16 weeks to as much as greater than 12 months. And the sample sizes range from a little over 300 to over 117,000. And the study dropout rates prior to follow-up ranges from 5% to 52%. Again, since all these studies are brought together in a systematic review and meta-analysis, they are answering a clinical question, which is there any association between the duration of breastfeeding and the risk of childhood obesity? But each study is different from another study. And we're concerned about whether, for example, the duration for breastfeeding is associated with the association you're going to see. Okay? Here is another example. This example examined the risk of ischemic stroke in people with migraine headache. So, and the authors wrote, as seen in our descriptive tables, there was substantial variation in the sample sizes and characteristics of the research subjects across studies. Subjects were drawn from registries, administrative databases, randomized controlled trial participants, hospitals, and the community. These various source populations would be expected to be associated with different baseline risk of stroke. And the studies also varied in mean age of subjects, which ranged from 15 to 97 years, but most focused on the 15 to 50-year-old range group. Again, the authors are concerned about the age distribution from these studies, so the younger population group will, based on our knowledge, have lower risk of stroke, right, comparing to the older population. And that's why the association you're going to see between the migraine headache and stroke might be different from study to study. Careful qualitative synthesis of the data usually would indicate that there are diversities clinically and methodologically, and they may lead to variations in the magnitude of the effect size. We call this variation underlying the effects heterogeneity. So heterogeneity refers to the clinical methodological diversities among a set of studies. And what can we do about heterogeneity? Well, if the studies are too different, let's say we're really comparing apples and oranges, we don't have to do a meta-analysis. Remember the first slide I said meta-analysis is only an optional component of a systematic review. If they don't belong together in a meta-analysis, you don't put them together. You can report the estimates from those individual studies. Or we could seek to explain why the studies are different. So let's say, again, the vitamin D and placebo example. All the characteristics could look very similar, but the differences is in the vitamin D dose. Well, then we can do additional analysis trying to figure out if the effect size from vitamin D is associated with the dose. If there are no good explanations, or we cannot figure out a reasonable reason that why these effects are different, we could allow for it without explaining it. And the way to allow for it is through a random effects meta-analysis. Under the random effects model, we assume there's a distribution of true effects. Remember the assumption under the fixed effect model, we assume all studies are identical and there's only one true effect. So here, instead, we assume there's a distribution of them. So again, the circles represent the true effect in studies. We're using the same example. There are 3 studies, so we have 3 circles, the true effect. And under the random effects model, these 3 circles no longer coincide with each other. Now there is a distribution. So if you look at the little normal curve underneath the circles, that's the distribution of the true effect size from those 3 studies. And in contrast, if you still remember the plot from the fixed effect model, all the 3 circles coincide or overlap each other. And again, using the same notation, the observed effect size in study 3, the Y3, now differs from the true effect in study 3 by that epsilon, so the error term within that study. But because the study, we're assuming the true effect size follow a distribution, there's one more source of variability. Okay? So the variability is denoted as theta 3 here. And instead of having only the within study error, the true effect in study 3, the Y3, can now be written as the mu plus the zeta 3 plus the epsilon 3. Again, the Y3, the 0.4, can be written out as using the mean of the distribution of true effects among a population of studies, plus the zeta 3, which is the difference from the true effect in study 3 from the overall true effects, plus the error term in that study. Here's another way to look at it. Here, the Y3 can be written as the mu plus zeta 3 plus epsilon 3. Now, the distance between the overall mean and the observed effect in any given study consists of 2 distinct parts: the true variation in effect sizes, which is the zeta i's, and the sampling error, epsilon i's, within the study. More generally, the observed effect yi for any given study can be written as a grand mean plus the deviation of the study's true effect from the grand mean and the sampling error in that study. So now, Because we have assumed all the circles, again, going back to the circles, which are the true effect in each individual studies, there's a distribution, okay? So there are two sources of variance. The first source, if we just focus one study, there's winning study variance. So the distance from the theta I, the circle, to the yi, the square, depends on the winning study variance. So the variance is the random errors winning that study. That's the winning study variance. And we have that. We have exactly the same winning study variance from our fixed effect model. On top of that, there's another level of variance, which is the between study variance. Okay, so the distance from the mu, the triangle, to each theta I, the circles, depends on the variance of the distribution of the true effects across studies. And we call that variance tau square. So because all the circles, again, the circles on this plot, they're the true effects in each study, because they don't line up together, they don't coincide with each other, there's a distribution. And that distribution is the between study variance. So under a random effects model, we have to capture both sources of variance, the winning study variance as well as the between study variance. So here's a nice contrast of the fixed effect model and the random effects model. Okay, the different assumptions you're making. Again, if there's only one thing you're going to take away from this section of the lecture is this slide, the different assumptions underneath two different models for meta-analysis. On the left-hand side, all three figures, you have seen all of them, and they are the assumptions for the fixed effects model. There's only one assumption, and they're showing in three different ways. So under the fixed effect model, we assume all the studies share a common true effect size. That's why all the three circles lie on top of each other. So there's only one identical common effect size. However, under the random effects model, if you look at the figure on the upper right-hand corner, there is a distribution. So the three circles no longer line together. There's a distribution of effect size, okay? And because of that distribution, we added one more level of variability, which is the between study variance. And that's why you have to capture them in your analysis using the two slightly different equations. So under the fixed effect model, yi equals theta plus your error term winning study. However, under the random effects model, the yi equals the mu, the grand mean, plus the zi, that captures the distance of each circle from that triangle, plus the epsilon I, the error term. Again, the difference is under the fixed effect model, there's one source of variance. If you look at the last set of figures, right, there's only one source of variance, which is captured by that normal curve for each study. However, under the random effects model, we actually have one more layer, which is the variance between studies. That's why you have 4 normal curves instead of 3. We still have that winning study variance, but however, underneath the last plot, that little curve shows you the variability, right? The distribution of the true effect size. That's your between study variance. Now let's take a pause for a moment. Well, what are we trying to do? What are you going to observe from the study? You have 3 studies, right? And the data you observe are actually, always the same. You will get a risk ratio estimate, odds ratio, plus some variance from that study, right? So you observe the amount of information or data you have in hand will stay the same, regardless of which model you're trying to use, okay? And the purpose of doing a meta-analysis, you're trying to use your data you have in hand and trying to guess where that center of the distribution or where that common effect size is. That's what you're trying to do a meta-analysis. And we're saying there are 2 different ways to get that number, get your meta-analytical results. Either assume the studies are identical, they're the same, then we're going to use a fixed effect model. If we cannot make that assumption, then we're going to use a random effects model by assuming, well, the studies are slightly different from one another, so we're going to assume the true effect size are not the same, but there's a distribution. So that's what you're doing. You're taking the data you collected from each individual study and trying to make a best guess where the common effect is. And that guess depends on how different or how similar the studies are. If they're identical, then go ahead, use the fixed effects model. If you cannot make that assumption, then you're better off with the random effects model. That leads us to the second session of the random effects model, which we're going to show you how to do it. performing a random effects meta-analysis, your goal for the analysis is we start with the observed effects and try to estimate the population effect. So I have repeated that idea over and over again. The observed effects, regardless of the model, they are the same. That's the data you collected from the study. And the goal is to use a collection of yi, which could be risk ratio, odds ratio, to estimate the overall mean mu. And how we're going to do it? Through meta-analysis. The overall mean is calculated as a weighted average. Again, it's just a weighted average. And the tricky part for the random effects model is figuring out the weight, right? Remember we said under a fixed effect model, the weight equals the inverse of the variance, yeah, which we're going to carry over that idea to the random effects meta-analysis. And now the weight is still equals to the inverse of the variance, but instead the variance has two components. One is the within study variance, one is the between study variance. So that's the difference. The only difference is how you're going to weight each study. The weight equals the inverse of the variance, but the variance is modified by the between study variance. Okay? So we use the tau square to modify the weights used to calculate the summary estimate. That's the difference between the random effects model and the fixed effect model when you're doing it. Okay, so let's look at these. Again, they're just a set of equations. They look awfully similar to the equations you have seen previously. However, we have stars to denote the weight. You start with the observed effects and try to estimate the population effect through computing a weighted mean. And the weight assigned to each study in a random effects meta-analysis equals to 1 over the variance. Now we have a little star here for the weight as well as the variance, which is different from the fixed effect model. Because we want to modify that variance, right? Because now the variance has the within study variance for each study I plus the estimate of the between study variance tau square. So that's the difference. So the red circle on this slide showed you the difference from this model to the fixed effect model. So here, the variance has two parts, the within study variance plus that tau square, which is an estimate of the between study variance. And all the other formulas and equations are the same. You have seen them, but remember to plug in the correct weight, which is the star, and that means you have accounted for the between study variance. So the weighted mean equals the summation yi times wi divided by the summation of wi. Exactly the same equation you have seen previously, but the wi has been modified. And you can do the variance and take a square root of that, you get the standard error. And again, you can use the estimate and the standard error to get the lower and upper limits for the confidence limits for the summary effect. You can do a z-test to test the null hypothesis that the center of the distribution mu is 0. From there, you can get the two-sided p-value. So everything on this slide, you have seen it previously, and the only difference is a little star placed in each equation, meaning here you have to account for the between study variability. Now let's talk about the tau square. So the within study variance, you will have that from each individual study. So let's say you get the odds ratio and the confidence interval from study 1, right? That confidence interval captures the within study variance. And you should know how to get from the confidence interval to the standard error for the log odds ratio. And you have that within study variance. So the tricky part or the difficult part is to get the between study variance. How we're going to estimate that between study variance? There are different ways to do it, and one of the most popular one in the literature is called the Dersimonian-Lade method, or the method of moment, a different name but the same thing. And here the tau square, the between study variance, equals to Q minus degrees of freedom divided by C. And again, you will see a set of equations of how to get your Q and how to get your C. But if you read the equations carefully, well, we know all those numbers, just a set of wi and yi. As long as we have the numbers from the studies, we can get the Q and C. And you can plug in the numbers into this equation to get the Q and C. And the degrees of freedom basically equals the number of study minus 1. Let's say you have 6 studies for meta-analysis, then the degrees of freedom would be 5. So that's it. You have to figure out a way to get your between study variance, and Dersimonian-Lade method is one of the most popular methods to do it. And here are the equations to do it. Just a caveat, if the number of studies is small, then the estimate of the tau square will have poor precision. What do we mean? Well, you're trying to guess the distribution with a set of studies, but you have only 3 studies, so your guess of that distribution won't be very precise, right? So that's the idea. Using the same example that we used under the fixed effect model, here the example, you have seen this data already. Here we have data from 6 studies. We have the treated group, the comparison group, and number of events and non-events for each study, okay? And based on those numbers, you can calculate the odds ratio and the log odds ratio, which is the effect size on the second table in this slide. So we get the odds ratio, we take the log of that number, we get the effect size. And we have done the variance winning studies based on the fixed effect model, right? And here we can take the inverse of that number, get the weight, and you can do all this calculation, again, not by hand, hopefully, but using some statistical software or even Excel spreadsheet. Here, again, you want to focus on the summation of those numbers, as that's what's required for your equation, okay? So with all those numbers, we're going to take those numbers and plug them into the formula to get our estimate of the tau square. Okay, on the left-hand side of this slide, those are the equations I showed previously to get your tau square. Okay, tau square equals Q minus degrees of freedom divided by C, and there are a bunch of equations to get to that point. But the point is, from the previous slide with the numbers, we can plug in those numbers into these equations and try to get the tau square. And we have those numbers from the previous slide. So the tau square for this particular meta-analysis equals 0.173. What is tau square? Tau square is an estimate of the between study variance. Here we have 6 studies to estimate that tau square. Now we have the between study variance, right? Which is 0.173. And there's only one between study variance because you're using a bunch of studies to calculate that tau square. So that's the column for your between study variance is 0.173 for every single study. And now you have the variance, which is the column to the left of the circled column. So you have the winning and you have the variance between, and now you can get the total variance. So we have the winning study variance as well as the between study variance. And the column on the right of the red circled column is basically the total variance. So that's the modified variance from that study. And from there, you get the weight. You can calculate the quantity using W times your effect size and get all the numbers on the rest of this slide. So it's easy. I think as long as you understand there are 2 components for your total variance, which is the winning study variance and the between study variance, and everything else, you can always look up the equations and figuring out how to do it. Fortunately, you don't have to do it by hand, and the statistical software will do it for you. But I want you to understand how these are derived, and you have a point of reference if you want to do it by hand, and you will be able to go back to the equations. Remember that the variance for each study is now the sum of the variance winning studies plus the variance between studies, okay? Again, I just want to repeat the most important difference between the random effects model and the fixed effect model. And the weight assigned to study 1 in a random effects meta-analysis now equals the variance winning plus the variance between. So the number from the previous slide is 0.185. That's the variance winning study 1. And the between study variance tau square, the estimate of that is 0.173. Okay, so now you're going to add up those 2 numbers, and using 1 divided by that number, you get the weight from the study 1. So the new weight, or the modified weight, assigned to study 1 under a random effects model is 2.793. That's the weight. So going back to the slide, that's how we got the weight for the first study. And you can do the same for the second, all the way to the 6th study. And that's how you get the modified weight for each individual study. Okay, now it's easy. You have seen this multiple times by now. And the meta-analysis, the meta-analytical result, the pooled estimate, basically is just the weighted mean. And you're going to take the yi and use that time your modified weight with the star. Remember, the star is the difference between the 2 models. and you're going to sum them up across all studies, and that's how you get the weighted mean. And again, you can plug in the number and get the variance, get the standard error, and then you can derive your 95% confidence interval for your weighted mean. So here I did it. You can always go back and try to see if you can get the same results by plugging those numbers. The odds ratio under the random effects model, the pooled odds ratio is 0.568, and the lower confidence limit is 0.355, and the upper confidence limit is 0.907. So, what is a random effects model? Here are some of the summary points that you're going to take away from this lecture. Under the random effects model, we assume the true effects in the studies have been sampled from a distribution of the true effects. So basically the idea, going back to the slide, where whether the circles from the studies would coincide or align on top of each other, or there's a distribution. That's the difference between the two models. When they're identical, lying on top of each other, that's the fixed effect model. When you're assuming they have been sampled from a distribution of true effects, then that's a random effects model. And the summary effect in our estimate of the mean of all relevant true effects, and we can test the null hypothesis, which is the mean of these effects is 0 for a difference, or whether that's 1 for a ratio. And the confidence interval for the random effects estimate indicates our uncertainty about the location of the center of the random effects distribution, not its width. So this is a difficult concept to grasp at a glance, but the idea is the confidence interval from your random effects model tells you how uncertain or how certain you are about the location of the center of that mean distribution. And our goal is to estimate the mean of the distribution, taking into account two sources of variance, the within and between. And here I contrast the output from the fixed effect model versus the random effects model. So on top of the first figure shows you the results from the fixed effect model, and the pooled odds ratio is 0.485 with a 95% confidence interval. And if you remember, the fourth study, the Lane study, takes up 41% of the weight based on a fixed effect model. And if you look at the same study under the random effects model, it takes up only 25% of the weight, right? So the random effects model basically assume all these studies have a distribution of effects, so you're adding another source of variance to each individual study. So the idea is the random effects model are pulling study or shrinking the estimate together. So the random effects model is giving a little bit of more weight to smaller study or cut a little bit of weight from the larger study. So it's basically pulling them towards the center. So under the random effects model, the pooled estimate is 0.568, and you have an estimate of the confidence interval. And I want to go back to the basic idea. So the basic idea is what? We have a bunch of studies, and in this example, 6 of them, and you have odds ratio from each individual study. So if you look at the second column from both figures, those are the odds ratio you get from individual study. Those are the data you collected as part of your data abstraction for your systematic review. Regardless of which model you're going to use, those numbers remain the same because that's the data from what you observed. And the only differences here is now we have the observed data. We're trying to guess, or we're trying to estimate where that diamond is. So the diamond is pooled estimate. We have 2 diamonds, one under the fixed effect model and one under the random effects model. By using these 2 different models, the diamond will lie slightly differently on the plot, and they will have a smaller, a little bit wider confidence interval. As you can imagine, on the random effects model, you're less certain about the center of the diamond because now you're saying we have 2 sources of variation. One is the within, one is the between. So your data you have has been partitioned to estimate those 2 sources of variation. That's why it's a little bit wider than the fixed effect model. So again, you're using what you observed to figure out where the diamond is, and you can do it through making 2 different assumptions. One is all the studies are identical. That's why I'm getting a very precise estimate under the fixed effect. Or you're saying the studies are slightly different from one another. That's usually the case. That's why you're getting a less precise estimate under the random effects model. So I have said this multiple times. Under the fixed effect model, you assume that true effect is the same in each study and that the only reason for variation in estimates between studies is sampling error. Going back to the previous example, all the differences in odds ratio you're seeing from the previous example under a fixed effect model is because of the sampling error. However, under the random effects model, the model is trying to estimate a mean effect about which it is assumed that the true study effects vary. So again, the idea is you assume that all these studies are estimating an effect, but there's a variation between study. We have covered in this lecture what is a fixed effect model and what is a random effects model. Those are the two models you're going to see in the literature when people are trying to put studies into a meta-analysis. We haven't talked about which model to use, whether a fixed or random, and we haven't really talked about how to quantify the amount of statistical heterogeneity. We said based on your qualitative analysis, you're going to see the studies are slightly different from one another. How can we quantify that statistically? Can we come up with a number to say how much different they are different? And we're going to talk about how to explore the sources of heterogeneity, for example, through using meta-regression and subgroup analysis. We will cover these topics in upcoming lectures. And thank you for today. We have covered a lot, and I hope you have learned a lot, and we will be here to address your questions.